Hello students, in previous lecture we have studied about the crystal defects. Then there are generally three types of crystal defects are there. That is stoichiometric crystal defect, non-stoichiometric crystal defect and impurity crystal defect. We have already discussed about the different types of stoichiometric defects, that is vacancy defect, self-interstitial defect, as well as Schottky defect and Frankel defect. Today we are going to discuss about the impurity defect. See here, impurity defects. That impurity defects which obtained due to the foreign atom. Then what is foreign atom? Foreign atom is the atom of impurity, that is atom of another substance when added into the given crystalline substance. That is called as foreign atom. Then see here, for example, suppose there is a crystal of copper is taken in which those are the particles of copper, and those particles of copper is known as host atom. Host atom, it is the atom of that substance originally present in that crystal lattice. That means suppose 1 gram copper is taken, then there is the arrangement of copper atoms. Copper atoms are there in the crystal lattice of that given amount of crystalline copper. And here if we added the zinc material or zinc metal into copper, then here that copper atom which is replaced by zinc atom. Here the copper atoms from the original crystal lattice, it is displaced by zinc atom. Then see here, in this crystalline substance, copper atoms which are arranged in the crystalline substance, that copper atoms are known as host atom. Here copper atom are host atom, and that zinc atom which is known as foreign atom. Foreign atom, that is zinc atoms are the foreign atoms. Then the impurity defect which is arises, which is produced due to the foreign atom which is present in the given crystalline lattice. That means here zinc atom which is a impurity of zinc is added into the copper atom. Then here the original atoms of copper atom, that are few or copper atoms are displaced by zinc atom. Then here copper atoms are host atom and zinc atoms which are foreign atoms. And here impurity defect is arises or produced in the crystal lattice. And generally those impurity defects are of two types. There are two types of impurity defects are there. Two types of impurity defects are there. Then first one, that is substitutional impurity defect. Impurity defect. And second one, that is here interstitial impurity defect. We have already studied about the self-interstitial elemental crystal defects. That is the one of the type of stoichiometric crystal defect. And here interstitial impurity defect is there, which is a type, one of the type of impurity defect. Then see here the substitutional impurity defect, in which the foreign atom that is impurity, atom of that impurity, which displaces the host atom from its original site, from the crystal lattice. That means, for example, the alloy of brass which is taken, see here, alloy of brass, here brass which is made up of copper and zinc, and here host atom is copper. That means here the in brass copper atoms are there, but here the copper atom, those are replaced from its original sites, and here zinc atoms which occupies the space of that copper atom here, and therefore here substitutional impurity defect is obtained in this type of crystal lattice. And one of the example of that is solid solution, which is a alloys. Solid solutions are known as alloys. Alloys are nothing but it is a mixture of two or more different metals or metal and non-metals. Brass is one of the alloy of copper and zinc, in which the copper atoms are displaced from its original site, and that site zinc atoms which occupies that site of copper atom, which is a host atom, and that type of defect is called as substitutional impurity defect, because here copper atoms are substituted by zinc atom from its original site, and that is the one of the example of that substitutional impurity defect. Then one more concept is there, that is vacancy through aliovalent impurity. See here, vacancy means vacant place, empty place, which is obtained, that vacant place which is obtained because of aliovalent impurity. That means here the impurity of the substance which is added into the original crystalline substance, if that impurity which contains the cations with another oxidation state than the ions which is present with oxidation state of original cations, original ions, that is oxidation state of original ions present in the crystalline substance. For example, see here, during crystallization of NaCl, that is crystallization of NaCl takes place. During this process, if SrCl2 impurity is added into the NaCl crystals, that means here the original NaCl crystals in which there are cations and anions which are arranged in a specific manner in the NaCl crystals, that is here Na plus ion, Cl minus ions, which are arranged alternately in the crystal of NaCl. And during the crystallization of NaCl, this process here, if impurity of SrCl2 Cl2 takes place. Then here that SrCl2, that is strontium chloride, if added into the crystals of that NaCl, then that strontium having the oxidation state, that is strontium ion, which is Sr2 plus, having oxidation state +2, and here the original host ion which having the oxidation state, that is Na plus ion, which having oxidation state, that is +1, and here if strontium chloride is added into the crystals of NaCl, then here one of the Na plus cation, that is Na plus ion, that is cation of sodium, which is substituted by Sr2 plus ion, and here the ion with +1 oxidation state is displaced by the ion with +2 oxidation state, and therefore to maintain the electrical neutrality, one of the Na plus ion is also missing from another site, and here vacancy which is created, due to the displacement of that Sr2 plus ion. The charges get balanced because here 2 Na plus ion which is displaced by 1 Sr2 plus ion. Therefore here the charges get balanced. Therefore if this type of impurity defect is obtained or produced in the crystalline substance, electrical neutrality is maintained. That means it is electrically neutral. Then that defect is called as vacancy through oleovalent impurity. Oleovalent impurity means the impurity which contains the oxidation state which is different than the oxidation state of ion which is present in the host particles. That is about the vacancy through oleovalent. Then one more type of that impurity defect, that is interstitial impurity defect. Then see here the interstitial impurity defect, which itself indicates that in this type of defect, atom which can occupy the interstitial space. For example, see here example of interstitial impurity defect, that is one of the alloy, that is steel. It is a alloy of iron, carbon particles, nickel and chromium. Iron particles are the host atoms in which if impurity of carbon is added to produce the steel alloy, in the production of steel alloy, carbon particles when added into the iron, then that is size of iron particle is more, and here carbon particle, size of carbon particle which is smaller, and size of here host atom, that is Fe, is bigger. Those carbon particles which can occupy the interstitial space of the host atom which is created by the host atom present in the crystalline substance, present in the metallic crystal. Then see here, those are the interstitial space in which carbon particles occupies those interstitial space. And here formation of steel alloy takes place, and that type of defect is called as, that is interstitial impurity defect. As well as the third one type of defect, that is non-stoichiometric defects. Non-stoichiometric defects. First of all, we have to remind stoichiometry and non-stoichiometry. Stoichiometry, that means any compound, any chemical compound, for example NaCl, CaF2, NaNO3, K2SO4. See here, any compound in which there is a whole number ratio of their constituent atoms or particles. For example, in NaCl, Na plus ion and Cl minus ion, the ratio of that cation and anion, that is constituent particles, is 1:1, and that ratio of that constituent particle present in the crystalline substance is, that is 1:1. That means it is a whole number. That means there is a stoichiometric ratio is there. And here in CaF2 it is 1:2, as well as here NaNO3 it is a 1:1:3, and in K2SO4 here 2:1:4. That means here ratio of constituent particles in the crystalline substance is whole number ratio, is called as stoichiometric ratio, and that stoichiometric ratio changes to, that is non-stoichiometric ratio. For ratio of the constituent particles is not in whole number ratio, then it is a non-stoichiometric ratio of that constituent particles. Then we will discuss about that and the different types of non-stoichiometric defects. Then in this type of defect, the stoichiometry of the constituent particles present in the original crystalline substance, it changes, but here the crystal structure and chemical property of that substance does not changes. Chemical properties does not changes, it remains unchanged. That means here only stoichiometric ratio of that constituent particles changes in this type of defect. There are two types of non-stoichiometric defects, that is metal deficiency defect, and another one, that is metal excess defect. That are the two different types of non-stoichiometric defect. The first, in metal deficiency defect, this type of defect which is shown or observed in those type of compounds in which metal, the constituent metal particle which shows the variable oxidation state. Then what is variable oxidation state? All of you studied about it in the transition elements. Then transition elements which shows the variable oxidation state, that is here first scandium which shows +2 and +3 oxidation state, nickel which shows +2, +3, +4 oxidation state, iron which shows +2, +3, +4, +5, +6 oxidation state. That are the variable oxidation state shown by the D block element, that is transition metals. The positive ions of metal ions, that is cations of metals, which is replaced by cation of metal with higher oxidation state. That means see here in NiO crystal. Then see here, in nickel oxide crystalline substance, the ratio of Ni2 plus ion and O2 minus ion, that is 1:1. See here, in NiO crystal, that is nickel oxide crystalline substance, the ratio of Ni2 plus ion with O2 minus ion, that is cation is with anion, is 1:1. Then see here, 3 Ni2 plus ions which is replaced by 2 Ni3 plus ions. See here, 2 Ni3 plus ions. That means 3 Ni2 plus ion which is displaced by 2 ions of Ni3 plus. Then see here, Ni2 plus which is a host ion, and here Ni3 plus with the higher oxidation state ion of nickel itself, that is nickel, which displaces the Ni2 plus ions from two different sides, and to maintain the electrical neutrality, therefore one more site which produces the vacancy into it, and therefore one of the Ni2 plus ion which is missing, or which creates the vacancy on another site. And here chemical composition of, that is cation is to anion, that is Ni2 plus and Cl minus ion, that is chemical ratio of the chemical here chemical compound. Then here the ratio of that cation is to anion, therefore here ratio of cation is to anion or chemical compound, that is nickel oxide, which becomes Ni.97 is to, that is O1, that is 1.0. That means here every one atom of oxygen there is 0.97 nickel ion is per, that is then here chemical compound with ratio of that nickel and oxygen constituent ion, that is Ni 0.97 is to oxygen 1. Then that is the chemical compound, the ratio of chemical compound which becomes, that is Ni 0.97 and oxygen 1. Here that ratio of that constituent cation and anion or particles changes into non-stoichiometric ratio, and that is the metal deficiency defect. Metal deficiency, that means here Ni2 plus ion which is missing from its original site, and that is the metal deficiency defect. Then see here metal excess defect is another type of non-stoichiometric defect, in which there are two subtypes are there, that is metal excess defect which is produced due to the neutral atoms, and second one, that is extra cations or positive ions which occupy the interstitial space. That means if the neutral atom which occupies the interstitial space, then metal excess defect is obtained there, or extra positive ions which occupies the interstitial space, then metal excess defect is also produced there. The example of that is ZnO, that is zinc oxide. In zinc oxide, cations of Zn2 plus ions are there, and O2 minus ions which are arranged alternately. Then see here, example of this is zinc oxide, in which Zn2 plus cations and O2 minus anions are arranged here in this crystal lattice. If zinc atom which occupies the interstitial space, extra zinc atom which occupies the interstitial space, then here metal excess defect is produced here. But when this crystalline substance, if it is heated, then that zinc atom, it loses electrons and it forms Zn2 plus ions. That means it converted into Zn2 plus ions, and therefore here when that crystalline substance, that metal excess defect which is produced due to the neutral zinc atom here in this defect, then that zinc atom is converted into Zn2 plus ion. That excess Zn2 plus ion is there, and the loss of electrons, 2 electrons are there. Those 2 electrons occupies also interstitial space, and that defect is called as metal excess defect. It is due to extra positive ion. Extra positive Zn2 plus ion is present at interstitial space. That is called as metal excess defect produced due to neutral atoms or extra positive ions in the interstitial space. Then last term, that is by anionic vacancies. Anionic vacancies, or it is known as F centers, or it is also known as color centers. Color centers. Then see here, by anionic vacancies, that means here vacancy which is produced due to anion in the crystalline substance. Then see here, for example, when NaCl crystals, if it is heated in the sodium vapors, sodium in presence of sodium vapors, and that sodium vapors which contains Na sodium atoms are there, and NaCl which contains Na plus and Cl minus ions are there. Then see here in the figure that Na plus ion and Cl minus ions which are arranged alternately, in which when that NaCl crystal heated in presence of sodium vapors, then the sodium atom from vapors which combines with Cl minus ion present in the crystalline substance, and here that sodium ion which loses electrons and it becomes Na plus ion and forms NaCl crystal, and here that sodium vapors which get deposited on the crystalline substances and which creates the vacancy due to the anion, that is Cl minus ion, and here electron which loosened by the sodium ion, the electron which is loosed by sodium ion which occupy the vacancy. That see here, the electron which is loosened by sodium atom which occupies the hole, and therefore that hole is known as F center or color center. Why it is called as color center? Because here NaCl crystal originally it is colorless. It is colorless, and when it is heated in sodium vapors, then that defect is produced due to the absence of or due to the displacement of that Cl minus ion, and that hole which is produced due to the Cl minus ion that occupied by the mobile electron which is loosened by the sodium atom, and therefore that defective NaCl crystal which becomes yellow in color. That means colorless NaCl crystal changes to yellow NaCl crystalline substance when it is heated in sodium vapors due to the F center defect or color center defect, or the defect which is produced due to anion or vacancies produced due to anion are produced, and that is called as F center or color center, or vacancies produced due to the anion. It is also known as F centers or color centers. That is all about the impurity defects and their types, as well as non-stoichiometric defects and their types. Then you should solve the exercise of solid state in your textbook. Thank you.